Sunday. Thank you. So this is a topic that I like a lot. I think at least one person in the audience has heard some of this before. I gave a talk about this at Penn, that Wolfgang in the geometry seminar about 40-ish years ago. No, not quite that long, but that was an interesting experience. I hadn't been doing it that long, and to give a geometry talk in the seminar with Wolfgang, Dennis de Turk, Jerry Kasdan, Frank Warner, Herman Gluck, and Jean Calabi. That was an audience. So, and actually at the time, I knew enough about Cartan's method of equivalence to have done some new problems for myself, and enough that I could lie about it convincingly in a 1-hour talk, and actually little enough that I actually didn't realize all the lies I was telling. As I said, there's a lot more below the surface that I still hadn't come to at that point. So I want to try to give an overview of this material. So Cartan, actually I recently saw on the mathematics genealogy project that Cartan's PhD was not only supervised by Darboux, which I knew about, but co-supervised by Sophus Lee. And that thesis work was on the classification of Lie algebras, completing work that Lie had started and Killing continued. And Cartan did a tour de force addressing the rest. But then he began to work on the infinite continuous groups, which we now call Lie pseudogroups, and created an incredible panoply of technology to address these things. And regardless of the interest or lack of interest nowadays in the original problem of classifying Lie pseudogroups, this technology allowed it to answer and allows us to answer an absolutely fundamental problem, which is how can we tell when two geometric objects are the same up to a given group of transformations? How do you know that if you change variables, it won't look completely different? Now, I first slammed into this problem when I was writing my thesis up. At the end of my thesis, I was working on soliton equations and geometric features of things, and I was about to write a sentence saying this equation is, of course, different from this equation. And I thought, my God, how could I possibly know whether there's some diffeomorphism that relates to two? How would you go about proving such a thing or disproving it? Right? And a few months later, I got to Chapel Hill, my first job, and sat down talking to Robbie Gardner. And I mentioned this problem, which had really still was haunting me a little bit. I managed to find a fiddle in the thesis. I managed to find a sentence that was true incontrovertibly and avoid having to claim that these two equations were distinct. And when I told Robbie about this, he said, oh, well, Cartan solved that problem about 80 years ago. What? I mean, I was absolutely astounded. And then and there, we sort of mapped out a research program and said, look, if you can explain to me how that works, I can just bring you a truckload of problems that are really going to be interesting that we can attack with that technology. Well, that was a little bit premature because the complete understanding of those things took a little while longer to do. But it was so here are some examples that I've been involved in. Aircraft flight control systems are nonlinear. Right? That's not the fault of Newton. It's the fault of airplane designers, aircraft designers. They put the controls where they can. The controller, if it was uncontrolled, it would be Newton's equations, but that wouldn't be much fun to fly in. So the controlled system has forcings that are applied to effectuate the motion you want, and you end up with a nonlinear system. Well, in the early 80s, Hunt, Su, and Meyer found that with the right type of feedback transformation, you could actually linearize the system. So in the early days of looking at these things, I often felt it slightly artificial. Here's an equation which is simple, y double prime equals 0. But if you really mess up the coordinates, you can make it very hard to know what the solutions are. But here nature is messing up the coordinates for you. The complicated thing is the thing you walk in to see. And the simple thing is hidden inside it. Okay? And it turns out that the essential feature here is geometry. The system's linearizable by feedback precisely when it has the same infinite pseudogroup of symmetries that the linear system has. And that's not just a nice mathematical formulation. Robbie Gardner and I showed that it gives you an algorithm for the minimal amount of integration you need to do to find those linearizing coordinates. Okay. Suppose I give you a second order scalar dynamical system. Is it Hamiltonian? Well, if it's in the wrong coordinates, you may have a hard time deciding. But there are two invariants whose vanishing guarantees that it's Hamiltonian and vice versa. So whenever we look at, sometimes pure mathematicians have the luxury of having a purely abstract formulation of their equations and can even discuss solutions. But it's much more common that we actually have to write down equations in coordinates, and if we're solving numerically, there's no choice whatsoever. You have to choose coordinates. How much of the features are intrinsic? How much depend on the coordinates? Well, again, quite a few years ago now, people realized when symplectic integrators started that bad choices of numerical schemes that didn't address the natural symmetries of the problem could produce catastrophically bad solutions. Solutions in quotes, because the scheme converged to something that had nothing to do with the actual physical system. Okay. So differential invariants are the intrinsic information. When they're available, they should be usable for numerical methods. So this most recent of our applications of this is in probability distributions, where the statisticians call the location scale group the affine group on a line is a natural transformation group to consider for univariate distributions. And there we find, using the method of equivalence, new limit theorems that weren't known before. Some very interesting new distributions given by rational functions that have some potential applications of wavelets, among other things, and also gives a completely new insight into the distributions of extreme value theory, if you know what those are. So these are all questions that are geometric in nature. And Cartan developed methods that provide the solutions to these questions. Now, in fact, in principle, the solutions go all the way back to Lie. He showed that differential invariants, which are functions of the data, so if you've got a differential equation, y double prime equals f of x, y prime, they're functions of f and its derivatives up to some finite order. Right? And the remaining information is symmetries. And in fact, Lie's whole program was designed to mimic the success of Galois theory but differential equations. So he was interested in using symmetries to solve differential equations. And in the case of ODEs, when you have enough symmetries, you can exactly integrate the equations. So this was the program, but and it led to differential algebra and many other things that have prospered since then. But when Lie left this program to his successors, many people were trying to, for example, he had classified the infinite continuous groups that acted on the plane. And many people worked simultaneously on trying to extend those classifications. Besides Cartan in France, there was Janet and Riquier. But Cartan built this magnificent machinery that applied to things far, far outside that particular problem. So he combined the differential invariants and symmetries in structure equations, which were algorithmically constructed for infinite Lie pseudogroups. Right. And so there's an algorithmic part of his process, and then a sort of, probably fair to say, semi-algorithmic part, the method of equivalence. Robert Bryant likes to say it's a roadmap, not an algorithm. You know, I think that's reasonable because, well, you always know what to do. You don't know if you can do it, and you don't know which branch of the road you should take. You need to have some kind of extra stimulus to decide these things sometimes. And sometimes you're faced with trying to normalize some invariance under a group action where the representation theory isn't worked out. You don't know what to do exactly. So, I mean, this topic has, in many ways, sort of fallen through the cracks. Cartan was a mystery to most, I think, of his contemporaries. His work was, I remember I think it was Herman Weil's obituary of Cartan said, this very, very hard to understand, very, very hard to understand. And in particular, Cartan was using ideas that we can now explain because a massive amount of formalism has been developed. Right? For example, jet bundles make it easy to describe these things in formal terms. Jet bundles were invented by one of Cartan's students, Erisman, but that was a few years after Cartan died. Okay. So this material was very poorly understood, and meanwhile, other people using powerful algebraic methods, Spencer, Kumpera, Hubert Goldsmith, and independently in Japan, Tanaka, took a new approach to the Lie pseudogroups. Okay. But one example that sort of burned into my memory is Singer and Sternberg. Okay, these are famous people. They're very bright people. They produced a paper which must have done more harm than good. The Infinite Groups of Elie and Cartan, Part 1. And I remember I finished my PhD in '78, I think. I remember at the time people saying, well, this stuff's pretty hard, you know. Singer and Sternberg published Part 1 in 1965 and haven't been heard of since. I haven't read this paper for a long time. I looked at this paper the summer that I was understanding Cartan's algorithm. And I was pretty unhappy with, I think it's a little bit of mathematical vandalism there, inadvertent maybe, but they put off an enormous number of people from this. And they actually say things that are so misguided you might as well say they're wrong in the paper. Okay, but I've never met Sternberg, and I haven't been in the same place as Singer since I found this out. So if I ever am, I want to ask him about this because I figure if I could figure it out in a month, they should have been able to do it in some time since 1965. Well, okay, so there's another part of this. This whole story, I'm going to tell you the story sort of from the beginning as the machinery was developed. That's not how I learned it. I think probably the only person alive that learned it that way is Robert Bryant. I think he just sat down at the Institute the first year he was out and read everything. And the Princeton Institute is wonderful. The library still has these sign-out cards. So you pull out a Cartan's Collected Works volume, whatever, you'll see the names of all the people who read it before you, and you probably know them all. I mean, I know them all. But Robbie and I dove into this in the middle. We dove into it with the equivalence method. That had some disadvantages because there are all sorts of mysterious things we wouldn't have puzzled over if we'd started at the beginning. But it had the advantage that I knew how to calculate equivalence problems. And not very many people at that time had ever done that. After Cartan, Chern, as a postdoc, did this massive computation. And I remember talking to him again and again and again about that in the first year at MSRI. He didn't have an algorithmic approach to it. He had this brute force ability to do incredible algebraic computations, probably in his head. Right? And that's how he got through it. A few of Chern's students had solved equivalence problems. Paulette Lieberman, Erisman's student, so Cartan's granddaughter. had solved an equivalent, I think one equivalence problem. So not many people knew how to do this. And when the part of that I said was wrong in Singer and Sternberg was a place where they basically said, well, there's no interesting cases for ODEs, right? Because you can always rectify the vector field. Well, not with an arbitrary diffeomorphism group, you can't. You have to have enough room to make those transformations. And so I was able to make a simple example. And because I could solve the equivalence problem, I could see that there were invariants, right, for even an equation, a first-order equation, for single first-order ODE. So what they said was wrong about that, because they probably couldn't solve an equivalence problem. And at the time, it probably didn't occur to them that the example would be appropriate. This was the height of the Bourbaki era. Okay. So the first thing that Cartan had to deal with was a big hole in what Lie had done, because there was no theory to fill it. So the pseudogroups, finite or infinite, were all defined as the general solution of a system of real analytic differential equations. Ordinary in the finite case, PDEs in the infinite case. Okay. But everything's real analytic. Okay? So you can differentiate to your heart's content. In fact, people really thought about these things in terms of power series. What else would they do? Right? But in the ODE case, Lie had no way of dealing with the problem that arises, because you can differentiate the equations. They're partial differential equations. You have equality of mixed partials that can produce new equations. And they can produce new equations of lower order, okay, that you didn't know were there. So Lie had to assume that the system had been organized so that none of that could happen. Well, that's a reasonable thing to say, but there's no way to do it. You have no way, in general, of checking whether that's satisfied. So here's a system due to Maurice Janet, one of Cartan's contemporaries. So this is a single function of 3 variables. Of course, you could make it part of what looked like a transformation group. But it's been cooked up in a way that after you differentiate twice, where you ought to be seeing 4th order equations, you actually get a new one of 3rd order. And it gets worse. It just keeps getting worse as you take more and more derivatives until you eventually find out that this is actually an ODE. The solution depends on 12 arbitrary constants. Okay. And I think you have to prolong 3 or 4 times before you discover that. Right? And so without a theory behind you, this is a very big hole. So Cartan began with the paper in 1899 on exterior differential systems, where he extended the existing theory for differential equations defined by one form, vanishing a bunch of one forms. Okay. And he developed this purely algebraic test for involutivity that ensures that you can't get any new equations. After you reach an involutive stage, you know you're done. And he actually showed, in almost complete generality, but not quite, that after a finite number of prolongations, this process would terminate. And again, after he was dead, Kuranishi in mid-50s polished off the rest of the missing bits. Right? So this is a theorem. Of course, it just tells you you're doing the right thing. It doesn't tell you how many decades you might spend doing it. It's just a guarantee that eventually it will stop. So in the case of involutive systems, with an independence condition, I should have said, basically the involutivity test tells you that at the linear level, integral manifolds, so tangent spaces, fit together so that you can always extend a one-dimensional one, a line to a plane, to a 3, and so on. And so this is built for Cauchy problems. Sorry, you flow off of the lower dimension to get up one dimension. And the Cauchy-Kovalevsky theorem can be applied in the real analytic case to get existence and uniqueness, existence and degree of non-uniqueness, if you like, tell you how many arbitrary functions you can specify in these solutions. Right. So that all, of course, it does much more, but it filled this particular gap that had been left in the work that Lie did. So Cartan always started with the finite equations, the differential equations. Right? And he developed from that a collection of one forms. This part is purely algorithmic, absolutely purely algorithmic. Don't tell Singer and Sternberg. Right. So here's an example we'll use later. The affine group on the line, that's just y double, the general solution of y double prime equals 0. So, of course, we write that as a first order system. We write it as a pair of one forms. Right? And there's an independence condition. We're only interested in solution curves on which dx is not 0. Right? And there's the group. Now, from that, Cartan has a piece of the algorithm which I won't try to explain today, but it's once you understand it, it's maddening that you didn't immediately. So you can do this all all formally on jet spaces. So I did this a very hard work of a month in around 1984, if I remember right, and it's been published. But it's sitting there in Cartan, okay, just waiting for you to read it. So he gets rid of all the superfluous variables by setting them equal to an arbitrary constant, not too particular, it's sort of general constant. Because sometimes if you put something equal to 0, it behaves differently than others. But in this case, he's going to set y equal to constant, so of course dy is 0, so we can forget about y. We end up back on R2 with omega 1, which is just p dx. The exterior derivative of that gives us another form, dp over p. Okay, and so we get the Cartan structure equations. Right. So that's what you would get if you wrote down the matrix version of the affine group acting as on a hyperplane in R2. Okay, and do left. I never remember whether we're left or right invariant here, but one or the other is going to give you these structure equations. Okay, at least the dual. Okay, and as far as Cartan's concerned, the group is precisely the maps from R2 to R2 that preserve those forms. That's it. That's his definition of the group. Okay. So what is we see why does that work? Well, so just make another copy of those forms with bars on it, and ask what happens if I have a map from R2 to R2 that sends the barred ones to the unbarred ones. Well, p bar dx bar has to be p dx, right? Then dp bar over p bar has to be dp over p. Well, that tells you right away that phi can't depend on p. Okay? The x transformation has to have nothing but dx's in it. Right? So the left-hand side has to be equal to the right-hand side. Phi depends only on x. And p bar is given as a result by p over phi prime of x. But now the other equation, the next equation for dp, dp bar over p bar, tells you that phi prime must be a constant. Otherwise, there'd be a dx term floating around, and there isn't. Okay, so that's why phi double prime equals 0, and phi of x is the affine transformation. So this also shows Cartan's approach to subgroups was a key part of his classification of Lie pseudogroups. I mean, precisely the intransitive part that we're still waiting for Singer and Sternberg on is the part where they're invariant functions. Something that doesn't appear in the same way in the finite dimensional case. There can really be essential invariant functions in the infinite dimensional case. And so, but this illustrates, Cartan always views the subgroup as being cut out by preserving additional functions. So if we want to see the translation subgroup, well, that's the thing that preserves p. Right? P bar is P over A, where A is phi prime, right? So the only way that's preserved is if A is equal to 1. So you get the translation subgroup. Likewise, if you preserve X times P, it's only possible if B is equal to 0. So there's the other subgroup. Now, of course, there's nothing essential about these invariants, right? In this finite dimensional case, there's a perfectly well-defined subgroup. Even if you did never think about preserving invariants, you know that the two subgroups are there. But in the infinite dimensional case, this is a very important part of the story. So Cartan always, there was a lot of work to try to go directly from the infinitesimal version, right? The analog of the vector fields in the Lie, in the finite dimensional Lie group case, the algebra case. Cartan started directly with the defining equations and and went to his structure equations by his algorithm from that. So the whole thing was always to determine a collection of one forms where the transformations in the group are precisely those that preserve the one forms, right? And the structure equations look like this, right? The Aij rows are and the Cij k's are invariants, right? If they're all constant, these are the structure equations of a transitive Lie pseudogroup. If the A's are all 0, it's finite dimensional. And if not, there are arbitrary functions in the general solution. So next up, Cartan, in order to study subgroups, came up with his method of equivalence. So if you ever look at the paper on the subgroups of the infinite continuous groups, the first chapter is the method of equivalence. And it starts out in a way that I mean, must have mystified a lot of people. You want to find transformations that preserve a bunch of one forms, right? You have a map from the omegas to the capital omegas, and preserve a bunch of functions, and invariant functions. The little y's go to the big y's. Well, that's because for Cartan, the definition of the group was preserving the one forms, the special adapted coframe. And invariant functions are exactly what you need to preserve if you're going to have subgroups. So this whole thing was designed precisely for that purpose. But in fact, that's also the generic problem that you're faced with in using the method of equivalence. Unless you're very lucky, you actually have to face up to the entire thing. Right? That's what I didn't know when I gave this talk in the Penn geometry seminar all those years ago. So this is the method that Cartan uses to generate Lie's solution. He's very modest and so maybe Lie really was his advisor, I don't know. But he usually says, well, you know, Lie did all this before. I only added a little bit here and there. But in fact, he added an enormous amount. Very, very powerful machinery that you can use all over the place. So you often see moving frames. Cartan used moving coframes. It's the same process. Right? You're adapting the coframe to the aspects of the problem at hand. So there's a constant use of coframe adaptations, basically to identify integrability conditions. D squared equals 0, and the coframe adjustments. The process is exactly analogous to absorbing torsion in the case of a Riemannian metric. The coframe adjustments remove all of the inessential integrability conditions, and anything is left, you use a natural group action to try to normalize to constants. And that's where you make the transition from an algorithm to a roadmap. That can be challenging. Okay. But the process always produces things that look like this. Okay. And in fact, you're really looking at a system of differential equations. You want to find capital omega i's that pull back to the little omega i's. In other words, you want to solve differential equations, capital omega minus little omega equals 0. And you have to keep working until you either find an involutive system or you find a complete set of invariants. So the exceptional case, which is almost always interesting, the exceptional case is the ones that have the most symmetry. That's the one in which these invariants are all constants. Okay? And the symmetry group is finite if the a's are all 0 and infinite otherwise. So the other great thing about this differential forms version of things is the exterior derivative and d squared equals 0 are your friends. They just keep using them again and again and again. So if you have an invariant y, then dy has to be another one. So it's in invariant one form. You express it in terms of the invariant basis omega I. The coefficients have to be invariants. Well, how long can this go on? It can go on until you either get nothing new or you filled up a coordinate system's worth of invariants. So that's the generic case. You end up with differential invariants sufficient to form a local coordinate system. And in that case, there's no symmetry left. So in this generic case, once you get a coordinate system's worth, any further differentiations, again, produce invariants, but they're going to have to depend on the original ones. And those dependence relations are the rest of the intrinsic information. So if you have two systems, they all have the same invariants appearing in the same places. You don't have a map between them yet, right? But you don't need one to check these things. They're all completely independent of any transformation. Right? They're done independently in two different coframes. But you have to have the same invariants showing up in the same places in the structure equations, and you have to have the same dependence relations at the end. And if you do, then the transformation is precisely obtained by setting the invariants equal to each other. That's it. That's all the information. So here's an example that we looked at a long time ago. Single second order equation. I have a distinguished independent variable that I'm not changing. And I'm transforming a dependent variable in a way that can depend on x. And then you differentiate that to tell you how to transform the first derivative piece. Right? And since we're going to write this in terms of one forms, we don't need two derivatives. We do it on the one jets. Okay. So Cartan's approach to this produces, at the first sort of stopping point, the non-generic stopping point. There are three invariants. If they all vanish, the equation can be converted into y double prime equals 0. Right? If they don't all vanish, there's still very interesting information. If two of them vanish, then the system's actually Hamiltonian. There's a mechanical model in the right coordinates. The Hamiltonian is the sum of kinetic and potential energy. Right? These may be very weird-looking functions, but you have this mechanical analogy. Right? Precisely when these two invariants vanish. Okay. So with the same group, we can look at a special case of the Duffing oscillator. No forcing, no damping. I mean, the situation is very similar when you allow the damping, and then it's more complicated with the forcing term. But you get three differential invariants. Well, you're doing this on a two-space, so there are dependence relations among these invariants. But these invariants are, if you like, the intrinsic building blocks for the system. If you write, instead of the differential forms we would have started with before, you can write the system in terms of pick two of these these invariants. And all of the information you're obtaining that way is actually intrinsic. If you start with another coordinate system and do the same thing, the invariants that appear in the same locations in the structure equations will give you exactly the same form as these. Setting those two things equal to each other is the, well, the two independent ones, gives you the change of variable. But you have the option of using these, right, knowing that they're intrinsic. And in fact, one of the first things we were interested in this, and this is true in the damped case as well. It's not just the unforced undamped, so it's the simplest one to write down. But there are curves in the phase space where these differential invariants are also first integrals of the system. So that's a purely geometric property. And in fact, those curves know about the dynamics. Right? They have qualitative information about changes of the dynamics as the signs of the two parameters change. And we expect that this is still being looked at, but we expect that numerics based on those intrinsic functions will have advantages over an arbitrary approach to the problem. But again, that's a new issue. So another example, back to the affine group on the line, is the geometry given by univariate probability distributions. So we want transformations that actually preserve the distribution. So this is the case where we have an invariant to begin with. Right? The problem isn't over because the equivalence method coframe lives on R2. So we've got 2 degrees of freedom, but we have 1 invariant. All right. And you immediately get a second differential invariant, which is this. That's why I've used the logarithm. It simplifies the formula a little bit. It's the second derivative of log f divided by the first derivative squared. That's the second invariant. It depends only on x. Right? So it has to be dependent on the first one. It has to be a function of I. Right? And that dependence relation is the final piece of invariant information here. So, for example, you can ask what happens when the invariants are constant, and so on. I mean, there's a very nice characterization of the so-called extreme value distributions, which appear precisely the exceptional ones in the case of the product invariant I and j. And in addition to that, so that invariant's constant for the for the exceptional extreme value distributions. Those are actually as attractors, right? If you take a random a sample IID sample of random variables from a distribution and then look at the largest value that you pull out of that, right? And do that again and again and again. That largest value is distributed like the nth power of the original variable, okay, f to the n. And these are precisely the things that occur as in the limit as n goes to infinity. So the equivalence class of f to the n is the equivalence class is the same as f if and only if these invariants are constant. The distributions that have that property are attractors. They just gobble up everything around them, converge very quickly usually to these extreme value distributions as you compute higher and higher powers. And this invariant I times j gives you an intrinsic way of measuring the rate of convergence. You just look at this thing, evaluate it quantiles. Right? That's an invariant again. And the closer it is to the extreme value distribution's constant, the closer you are to converged to that limit. Right? That turns out to have a lot of interesting consequences. So another example from the same stable, if you like, is if you applied this instead of to the distribution itself to the omega function of the distribution, you get another limit theorem. There's a distribution that nobody'd heard of before that comes out as the attractor in that case. Right? And it has a lot of interesting properties, one of which is to generate a new bunch of univariate probability distributions on the finite interval that are actually defined by rational functions. Right? And they have the property that they're exactly equal to, integrate exactly to 1 on this interval. Right? And there's one for every integer. They converge to a, if you like, a delta function, but not the Euclidean, not the normal delta function. Something that has an entirely different character. Right. So, and we've started looking at the possible applications of that to wavelets, where it's like to generate probability distributions. Excuse me. And this is I think there were some number theoretic applications here as well. The coefficients that come up in these rational functions are just amazing looking, you see. And in this limit theorem, you get a new distribution, which is not that different looking from a normal distribution. It's close enough that I wonder whether there aren't, in fact, things in nature that are distributed that way that you couldn't tell the difference from normal with. But it does have, it has a distinctly different structure. In fact, it's given entirely in terms of exponential functions. And its standard deviation is a multiple of pi. So you get a probabilistic definition of pi using this thing. Okay. Anyway, there are many, many more applications. I don't want to try to go into details about any of them. The one old application uses this entire structure and produces the Gauss curvature. So this is something that it is an absolutely basic application of the theory that's gone before. If you put a metric on a surface in R3 in a diagonal form, it's only defined up to rotation, right? And the just by taking exterior derivatives, you arrive at this, and the absorption of torsion is the one you'll have seen in any geometry course, and it reduces to equation 13. Right? And now d squared equals 0 tells you something quite remarkable and very simple, right? Namely that the derivative of pi bar is congruent to 0 modulo omega 1 omega 2. So it's a multiple of omega 1 wedge omega 2. And that multiple, of course, is the Gauss curvature, because when you differentiate again, you get this identity that says k must be a function on this that drops to the surface. Otherwise, there'd be some extra differentials sticking out, and the exterior product with omega 1 and omega 2 wouldn't be 0. Okay. So that's one of the oldest ones. I guess I've never looked at Gauss's paper where he writes this down. I suspect it's more difficult than this, but then you can't have everything. So I think I'll stop there because my throat is running out of steam, but answer any questions people may have.
Thank you.
Yeah, sure. Sorry, was that?
No, the next one.
Okay, sorry.
Yeah,
oh, okay.
Just about, you said something about it, but
Yeah, sorry, I was.
the exact,
Okay, so here it is. So whenever a distribution has a mean, there's an alternative description to the usual probability density function or distribution or characteristic function, which is the omega function of f, which is defined to be integral from, say that the distributions on either of these limits could be infinity, right? But integral from a to x okay, so that's finite provided there's a mean. Right. Oops. Did I do that?
Generator should kick in, hopefully.
Yeah, the projector's still on.
So this is probably no break over. This is no break, but the generator should kick in.
Can you still see the board? Okay. Yeah, so if you raise the omega function to the power lambda, it's also an omega function. So there's a nice inversion formula that tells you how to reconstruct f given this. Okay, so raise it to the power lambda and produce another distribution f lambda. Okay, so the question is, when is the equivalence class of omega to the lambda equal to the equivalence class of omega? And the answer is there's exactly one distribution that satisfies that. It's called the CS distribution. It happens to be the same initials as Cascon and Shadwick, but don't let that. Yeah, so this is a distribution nobody's seen before. It's I mean, there are a lot of nice things about this approach. For example, if you, I mean, the omega function's 1 exactly at the mean. And its derivative at the mean is called the ohm. But that's actually half the mean absolute deviation. So this thing knows about how to measure spreads around the mean, even though there's no second moment needs to exist. So this is a very fundamental thing, which Gauss should have noticed, right? I mean, it just didn't get seen for 150 years after it ought to have. I mean, it doesn't need anything that wasn't available more or less at the time of Gauss. But anyway, so the limit theorem here produces this CS distribution, a symmetric distribution, that has a little fatter tails than a normal, but doesn't look that different, and not obvious that you could distinguish it between the two in most data sets, right? And so what happens if you, I mean, omega functions have this nice property. If you look at the uniform distribution on -1, 1, well, actually, what's the simplest case? So just the Bernoulli distribution. That has an omega function, right? Okay, and if you take powers of that, it eventually converges to this. Of course, the best way to see that is to let the domain spread out. But in fact, if you leave it where it is, you just get a delta function. But it's not the normal delta function, right? So the one invariant here is the ratio of the standard deviation to this ohm, right? And that's for the normal distribution, that's root 2 pi. For this distribution, it's pi times the root of 2/3. So they're different, and the delta functions know they're different. But if you do this for integer power, so if you take the Bernoulli omega function and raise it to an integer power, you get a distribution on the same interval, and it's given purely by rational functions. This inverse process gives you rational functions. I mean, you can do it for any power, but the integer ones give you rational functions. And the PDFs sit there on -1, 1. Now, they do funny things outside the interval, right? But they give you exactly integral 1 there. And so I think they're interesting. They are interesting. I'm not sure what they're completely what they're good for. But you could certainly imagine using these things in a wavelet analysis.
Comments or questions? Let's thank you again. Thank you very much.